Good afternoon, everybody. Really happy to be here, to see an actual physical audience with people, a physical speaker, and also people online, I think. So really happy you're all here. I'm also really happy and a little bit proud for this event, because this is the kickoff of the NanoSeminar series. So this will be taking place every second Thursday. There will be a talk, typically by an external person, expert in the field, who will talk about a topic of interest for the Institute. And typically, we will also then have a short talk before the main talk, which will be given by internal people from ICN2. So this is a great way of both seeing experts from outside the Institute and also to see your colleagues from the Institute, tell them about the work they are doing. So today's opening act will be done by Alex Mihu. He is a postdoc in the ultrafast dynamics and nanoscale systems group, which happened to be my group. So please, Jake, take it away.
Thank you. Good afternoon, everyone. Thanks for having me here. Today I'd like to talk to you about an optical technique that we've developed in our group, which allows us to study phonon heat transport with ultra-short pulses of light. So science isn't done in isolation, and so to begin I'd like to acknowledge all of the people that have worked on this project. They're from the ultra-fast dynamics group in nanoscale systems here at ICN2, led by Dr. Klaas-Jan Tillero, as well as the molecular nanophotonics group at ICFO, led by Professor Nick van Hulst. And I'd also like to thank our funding partners from BIST, from the Spanish government, as well as the ERC. So let's have a look at examples of diffusion. What is diffusion and where do we encounter it in real life? So in physics, we can think of it as heat conduction in materials. When we look at chemistry, we can think of the diffusion of concentrates, such as when you brew this cup of tea. And in biology, we can encounter it every day whilst we're breathing, during the removal of CO2 and the replenishment of oxygen. It's not just limited to the sciences, it also exists in other fields such as finance, where we can think of the diffusion of money or ideas. So if we think back to the process of heat conduction in physics, when we want to study the thermal properties of a sample, we want to study them by using small temperature rises so as not to change the sample that we wish to study. To study small changes, we need sensitive techniques. And one such technique is called pump probe microscopy. This optical technique, we use a pump, which is a short laser pulse, to excite a sample. And then a short while later, we use a second probe pulse to interrogate the sample and detect the changes. Okay. What's unique about this technique is that if we apply a periodic modulation to the pump, so in effect, we're turning the beam on and off in time. This modulation transfers into the reflected probe signal, giving us information about the sample. In this way, we are using a differential technique, which means that it's highly sensitive to very small changes. To gain information in time, we can change the time of arrival of these two pulses, which we call the pump and the probe. This is achieved by changing the path length that the light has to travel before it reaches the sample. By acquiring the signal at different time delays, we can build up images of the processes which are occurring in the sample. And if we stitch them together, we'll be able to create a movie of the dynamics of the system. For example, here, in this minus 10 picoseconds, we have the probe arriving before the pump. And this corresponds to almost zero signal in this graph here. When the pump and the probe arrive at the same time, corresponding to 0 picoseconds, we have a maximum in the signal, which at later times decays and returns back to its equilibrium state. So pump probe microscopy gives us information on the dynamical processes with high temporal resolution, with timescales from the femtoseconds to the nanosecond, and is highly sensitive, as I mentioned before, with differential signals down to 10 to the minus 7. An extension of this technique is called spatial temporal microscopy, where now we look at the pump and probe beams, which have both a spatial offset as well as the temporal offset. By scanning one of the laser beams with respect to the stationary other, we can build up a picture of the excitation within a sample. If we look at this for different time delays, we can see how this excitation changes. And what you see is that it starts off as a small region of the sample and gradually gets bigger and bigger in time as the excitation is diffusing out of the central region. So the diffusion is quantified from the broadening of the spatial profile with a resolution that's set by the signal to noise ratio of the data acquisition, not by the diffraction limit, which makes this a super resolution technique capable of resolving profiles that are broadened by tens of nanometers. However, you'll notice there's a missing panel in my movie reel here. And this missing panel corresponds to this scenario here, where the probe arrives before the pump. In normal spatial temporal microscopy, this is minimized as it represents accumulated signal and therefore obscures your ability to resolve dynamical processes in the other time frame. However, it also contains information about the previous pump pulse. This comes from the fact that we're not just sending, it's not a single shot experiment where we're sending just one pump and one probe, we're sending a continuous train of pulses. So when we talk about the probe arriving before the pump has reached it, we're actually sensitive to the remnant excitation from the previous pump pulse. So to reiterate, the probe arrives before the pump, is sensitive to excitation from the previous pump pulse, and this delay is now set by the pulse period, so the separation in time of adjacent pulses. With this, we're able to extend the technique to study processes occurring on the femtosecond to nanosecond scale with conventional, up to the microsecond scale with this pre-time zero spatial temporal technique. We propose to use this to study long-lived excitations, such as thermal transport in suspended films. So this is how the setup looks in our lab. If you're interested, I'd be happy to show you around it. Just let me know. So we have our technique, and we need to verify that it works. And to do this, we're going to use we'll use suspended atomically thin materials, one of which is shown here, molybdenum diselenide. These are van der Waals materials, which have many intriguing electrical, optical, and thermal properties, and have been used in a variety of next generation devices by building heterostructures with these materials, or by exploiting novel physics, such as the single photon emitters or the Valian spin physics available. Simply, in short, we basically exfoliate these thin flakes of the molybdenum diselenide, and we transfer them onto this substrate, which has a hole in the middle in this black region here. For more information about the specifics of how we do this, you can look at our recent technical note published in collaboration with the Photonics and Photonic Nanostructures group here at ICNT. Apologies, their logo is missing. So what if we look at the temporal dynamics of such a sample? Well, we have two regions of interest we can study. We have the supported, where it's in contact with the substrate, and the suspended. If we look in the supported region, we have a spike in the signal at time zero, which then decays over hundreds of picoseconds. This corresponds to an electronic excitation that decays in time, and you can see that the sample has returned to an equilibrium state by the time the next pulse arrives. If we look at the suspended region, we notice two things. We notice there's a large difference between the two plots. Firstly, we have a non-negligible pre-time zero signal, and secondly, that the signal itself is now negative. The negative signal comes from the fact that we now have a reduction in refractive index rather than an increase in the opposing case. This non-negligible pre-time zero signal comes from the accumulation of heat in the system. As the initial electronic excitation relaxes, it transfers its energy to the lattice system as heat, which can then diffuse out of the system. We can look by scanning the probe over the pump, we're able to map out the profile of these excitations, which we see for at time zero, we see the sharp profile, which then later decays, reducing in amplitude and becomes significantly broader. Intuitively, we can think of this as heat diffusing out of the system. The intuitive explanation here is, or the intuitive interpretation here, is that a broader pre-time zero profile corresponds to a larger thermal diffusivity. But if we look at these in more detail, by taking line cuts of the two profiles, we can see that in fact this time zero profile has a Gaussian shape which matches that of the incoming pump beam, and the width is the same. This initial excitation diffuses in space, and we end up with a much broader profile looking at the pre-time zero signal. On this plot here, we see the blue circles represent the actual data points, and the red line represents the model that we use to quantify the diffusivity. This broadening takes place whilst we're exciting the sample with low laser powers, which are leading to a temperature rise of the order of a few tens of Kelvin. So this is a very small perturbation to the system. What you will notice here is that the model is actually in excellent agreement with the experimental data, even to the edges where you see that the data and the model both go to zero at around 7.5 plus or minus 7.5 microns. This corresponds to the edge of our hole, which is where the material comes in contact with the substrate, which has been gold coated, ensuring that we have a perfect heat sink, and so we would expect the signal to go to zero here. This boundary condition of the perfect heat sink allows us, we use in our model to simulate the temperature profile for different diffusivities using the heat equation in 2D and with two input parameters, one being the diameter of the hole and the other being the beam diameters. The graph on the right shows that our earlier intuitive understanding of a broader profile corresponding to a higher diffusivity was correct, as we can resolve increases in the width of the spatial profile, which correspond to higher diffusivities. So this brings me to the main advantages of this technique. It's an all-optical non-contact technique with minimal sample fabrication. It has a simple model based on the heat equation, but importantly, this has no material input parameters like thickness or absorption. It's highly sensitive to small temperature changes and can detect diffusivities over several orders of magnitude. We verified the technique with another material system, tungsten diselenide, and we can compare our results with literature by converting the value for diffusivity into a value for thermal conductivity using the heat capacity. And we find that we're in excellent agreement with both theoretical and experimental works for both the molybdenum and tungsten diselenide samples. So finally, to summarize, diffusion is important for many physical, chemical, and biological processes. Spatial temporal techniques can study diffusion, but our pre-time zero technique can study the diffusion of heat that is spread in plane in thin films. With that, I'd like to thank you all for listening, and I'd be happy to answer any questions you might have.
Do we have any online questions?
No questions in the chat.
Okay. Any questions from the audience?
Yeah. So what is the time scale of the measurement? In the one that you showed that you have a temperature increment of 10K, that was done on the femtosecond regime, or it was microsecond regime? My question is, if this is related to the electronic temperature, or this is just the lattice vibration temperature, or if you can decouple both, and how that works in this technique.
This would be the lattice temperature. So the electronic temperature would be initially much higher, but then that energy relaxes and transfers to the lattice. So it'd be the lattice is 10 Kelvin higher.
And can you go to lower time scales and then measure the electronic temperature?
We can increase the fluence of the laser, so we can pump more energy into the sample, and we can increase the temperature of this, increase the temperature rise in the sample. The measurements are all done at room temperature, so we can't look at a low temperature behavior yet.
Even for the delta T equal to 0, you're still hitting the phonons, not the electrons.
Well, with delta T equals 0, the fluence would be close to 0.
I think it means the time delay. Time delay delta
Yeah.
T.
Yeah.
Oh, sorry.
Yeah, in this graph, the one that you said.
Yeah, at time 0 here, we would be putting all of the energy into the electronic system.
Right. Yeah.
Exactly. Which just at a later time will eventually return to the lattice.
Right. So you get the information from what you showed us from the width of the curves, but can you get the same information from the height?
The height's more complicated because you have the decay dynamics, which aren't necessarily related to the broadening dynamics.
I was wondering how. The second mic, please. Sorry? For the people that are listening. Okay. I was wondering how homogeneous has to be the thin film, and also if you have a limitation on the thickness of the film.
The films have to be optically transparent, so you could go up to hundreds of nanometers depending on the material. You can look at non-homogeneous materials, but as far as we'd understand, it would be if you had an in-plane anisotropy, you would be able to study that by looking in different directions or different scan directions.
But I meant limitation below. I mean, the minimum thickness, the height.
So we've actually measured these films down to the monolayer limit. So yeah, the ultimate. Yeah.
Thank you.
Yeah. So the variable that you measure is diffusivity, or you access the thermal conductivity, and if it's diffusivity, then you need the heat capacity, and how you deal with that.
So we extracted diffusivity, and at the moment we are taking the heat capacity from literature. I'm using that to convert to thermal conductivity. The reason we do that is because most other works publish the results in thermal conductivity, so to compare.
Okay.
Question from the chat.
Oh. Okay, thank you for your presentation. I have a question about the boundary condition used to simulate T of x. How Fourier's law explains the phonon transport? I'm not sure if you understood that question. I didn't.
No, I'm not sure.
Do you use Fourier's law?
I mean, yeah.
Yeah.
So we use Fourier's law to describe the thermal transport in the material. And in this material, the transport is by phonons. So at the
Maybe I can repeat the question for the home audience. So the question is about the boundary condition and whether or not you use Fourier law for diffusion. So I think you already gave the answer. So maybe you can specify the boundary condition that you have.
Yeah, go back a few slides. The boundary condition here, we impose that the temperature rise in the supported region has to be 0 for the pre-time 0 case. This is because we gold coat these samples, leading to efficient heat sinking, which means that the this kind of model condition matches the real life condition, which is quite important for this technique.
Okay, I think we can stop here. So let's thank Jake again.
Thank you.
And then we'll move on to the main event of today. So our speaker is Aitor Lopeandía. Hope I pronounced it correctly. So I'll describe briefly his career so far. So he is an associate professor of applied physics at the physics department here at the Autonoma. He's lecturing in physics and nanoscience and nanotechnology since 2010. He has a PhD in material sciences from 2007, also here from the Autonoma, working on nanocalorimetric devices. As a postdoc, he worked with some fellowships at the Institut Néel in Grenoble in France, also working on calorimetry. He received an ERG fellowship to return to the UAB as a lecturer professor, joining the group of nanomaterials and microsystems. And then since January 2021, he joined ICN2, our institute, as part of the GT&AM group. And his research interests are around the measurement of thermal properties and nanoscale materials and their applications in energy. So we're very happy to have you here.
Thank you.
And you have,
I have the microphone.
Okay.
I will start the presentation. Okay. Oh. Okay. We'll be here. Okay, thank you for the invitation. I will start in. Oh, so I had to start that type of seminars. I hope I fit with the idea of the seminars. As we are a new group here, what I have selected is a technique that can be easily used to measure 2D materials. It's a technique to measure thermal conductance and thermal conductivity, therefore. And I'm presenting here one, this is okay for the pointer. Sorry, the pointer is not. It's a mouse. I can change it now. Okay, don't worry. Then the idea is I will show how we can use phonons to investigate growth kinetics and phase transitions in ultrathin films in that case. Okay. Now we will try to monitor the growth of a film through the thermal conductance evolution of that film. I would say that, let me go back because I skipped something. It's true, I was starting from a different slide. I wanted to present the group first. No, this is what I wanted to say. Here is the group that we are joining, ICN2, where you have Javier, that is the leader of the group, and the rest of the colleagues. I would say that as Klaas was telling you, I would say that in the center of my research interest is the development of new techniques to measure nanoscopic samples and thermal properties of nanoscopic samples, and of course the possible applications in energy. I would say that we have been working quite hard in different fields. Heat capacity nanocalorimetry. We have developed systems able to measure heat capacity on samples below nanograms in scan areas of millimeters. It essentially means that we are able to measure very ultra thin films below the nanometer thickness of effective thickness. We have also developed different techniques to measure nanomaterials, nanoscale materials, either on, no, we cannot change that right now, either on nanowires with suspended structures, ultra-thin films or with suspended structures. And here I will try to focus on the Vauquelin methodology to measure ultra-thin films. And of course, as I said, that I will focus on that experiment that is the one that we will use to measure to monitor the growth of the samples during using thermal conductance. I would say that in situ growth monitoring is very interesting. It's very necessary to know. Okay, it's during the early stages of evaporation. All the phenomena that will happen is essential to know the growth process, to understand the microstructure and the overall processes, the overall properties that we can find in the material. I would say that there are many methodologies and measurement techniques to measure that information. I would say I'm mentioning here a few of them. That the wafer curvature, the mapping of a wafer curvature in order to monitor the stress evolution of the film, X-ray reflectivity, ellipsometry, low and medium energy electron diffraction, lit and mid, that are typically implemented in evaporator systems. And I would say that the most common and the most simple one is the resistance-based measurements. No? This is something that everybody can do in his lab. He's having an evaporator. He can prepare just a substrate that it should be an isolating substrate. No, like this one, I'm assuming a substrate where I can lithograph a couple of electrodes, of metallic electrodes, on top of on a high insulating substrate. The difference in electrical conductance in that case used to be around 10 to the 5 orders of magnitude between the metal and the oxide, the electric material. And I can say that in order to do that kind of measurements, we only need a power bank, no? And we only need a system, an SMAU, in order to measure, and we can monitor easily at least the threshold when the impingement between islands arrive, and we can detect that at that point. I would say that this is for sure interesting in order to identify that point. We can also measure phase transitions through the electrical resistivity, but this is for sure limited to materials that are highly conductive, no? Because we need to make the electrons to percolate through the islands. No? I would say we were wondering if we were developing that technique, the 3 omega Bocklane, that we were able to measure thermal conductance in the plane with extremely high resolution, and we wonder if we were able to perform exactly to replicate that experiment just using phonons as a proof. No? I would say that phonons, in contrast with electrons, no, are much more sensitive to film structure because of their large mean-free path compared to electrons. But of course, in order to do that kind of experiments, we require to have the control, no, and to have the structures, no, to substrate the bulk below the surface where we do the experiments. Essentially, because as a difference with electrical conductors, that we can find a couple of materials with a huge difference in electrical conductance. This is not that possible. This is not possible in the case of thermal conductance. Okay. It was already, then we will focus on the technique. It was already at the end of the 80s, it was close to the 90s, that Bocklane, Bocklane, was developing that system. It's a suspended membrane. It is a suspended membrane, okay. This is a suspended membrane. In that case, it was a combination of oxynitrides suspended on top of silicon with a central heater. He was promoting the central heater was defined right in the center with a longitudinal symmetry in order to heat the central part of the membrane and generate a temperature gradient, and to promote a heat flux direct from the center to the boundaries. No? In a steady state situation, if we introduce a constant power, it's very simple. If we introduce a constant power, I would say that we will generate that state, and we can extract directly the thermal conductance of the film. In that case, it was silicon nitride, the combination of silicon nitride and silicon dioxide layers. It was in 2012 that Olivier Bourgeois, he was my advisor in the Marie Curie Fellow in the Institut Nel. He was just implementing, coupling that Bocklane geometry, that longitudinal heater on top of a membrane, with 3D, I would say 3D dynamic methods, no? Just coupling in order to use logging strategies. The difference was essentially that you can remove huge amount of noise from the measurement, And he was improving the system. And at that moment, at the article he was publishing, he was getting, I would say, resolutions of delta k over k of 10 to the minus 3. It essentially means that depending on the thickness of the substrate layer, in that case was nitride, he was able to determine up to three significative digits in the precision of that method is pretty simple. Instead of inserting a constant power, what we do, or what he was doing, sorry, he was inserting an AC current with a 1 omega fundamental frequency. As soon as the power is released by Joule effect, what he was getting is a 2 omega power release, and therefore he was hitting the membrane at the same 2 omega frequency. That 2 omega heating produce on top of the base resistance produce a component, a variation of the resistance with a 2 omega component also. Combining the current, here we have an image or a simulated image where we have the central heater, and we have two proofs that are going to just to measure locally the voltage. No? Combining that current at 1 omega with that resistance that has a constant component plus the 2 omega oscillation around that constant, what we get is a voltage that has a 3 omega component plus the 1 omega component that of course we will like to remove, because all the information right here, what we can extract all the thermal information from the 3 omega component. That's the key point. No, I will not enter too much in details on the equations because But we saw that this is a very simple device that is very, I would say, close to the devices that we are used to fabricate in our group, the nanocalorimeters, following the same strategy, starting with a silicon wafer, with an oxidation, a thermal oxidation, and low pressure chemical vapor deposition of silicon nitride. We can get a combination of oxynitrides that are mechanically stable in order to place on top the heaters and to define the heaters with a very, I would say, for the moment, very simple microfabrication techniques. We can get membranes ranging from, and this is important, ranging from 40 to 450 nanometers. Depending on what we want to measure, we will have to target the very thin membranes or the thicker one. Most of the experiments that I will show right here are done on devices with membranes of silicon nitride membranes of 180 nanometers. And what we did is we tried to improve we did a finite element modeling in order to study the technique and to improve as much as possible the temperature profiles, because at the end is the temperature profile which will give here you can see the characteristical temperature profile that we have when we are heating the membrane, and in transversal, I'm getting a bit lost with the pointer. In transversal position, I would say at 90 degrees to the vertical direction, we have the red profile, and in the vertical direction we have the black profile. That is pretty flat, with few, I would say, less than few hundreds of millikelvin and of temperature gradients within the temperature line. We developed the measurement chain. Of course, all this system has to be in ultra high vacuum. We have a cancellation circuit. As I said, as a result of the heating, we have two components, two voltage components. One that is having the information, the thermal information of the system, and the other one that is just the one with the reference. And here we have a cancellation system that permits us to make differential measurements. And what we did is we developed an FPGA-based locking that permits us to fit with the correct frequencies, the measurements. This is a typical measurement done at 1 Hertz. It's important to say that this is done at 1 Hertz because I will show you later which is the dynamics of the system and why we do the measurement at 1 Hertz. This is the temperature, the DC temperature measured from the 1 omega signature. And in red, you can see the DC temperature, the temperature increase measured from the 2 omega, measured from the 3 omega voltage in that case, and this is the delta T 2 omega, as I said. This is measured at 1 Hertz. As I said, with measuring 3 omega at 1 Hertz, with the signal to noise ratio that we are getting right now is around 10 to the 5. It essentially means that we are not able only to see 3 digits, but we are able to see 5 digits of resolution in the thermal conductance, and therefore we have to transfer from thermal conductance to thermal conductivity, taking into account the geometrical factors. Okay, why I said 1 Hertz? Because, okay, of course, this is a typical comparison between the 2 omega. No, this is the fraction between the delta T 2 omega. I will explain which one is each one as a function of the delta TDC. At the moment we insert the power in the device is heated in average around, no, this is TDC, the device without heating is T0. No? As soon as we introduce a power, an oscillating power, in average the device will oscillate the temperature around a delta TDC. That delta TDC is always the same. It does not depend on the frequency, on the excitation frequency. What will change, and this is depending on the heat capacity of the membrane by itself, is the relation between the delta 2 omega, that is the amplitude of the oscillation temperature, as a function compared to the total. I would say that if we are heating very fast, if the frequency, the excitation frequency is very fast, the heat capacity will damp our oscillation and we will have a continuous heating, like a continuous heating. If we heat it very low, and this is within the modeling, within the design, to fix everything within the instrumentation that we have in the lab, now to fit that, and we are typically doing the experiments at I'm getting a bit lost with the pointer, around 0.9 Hertz. No? This is the typical frequency that we do the experiments. At 0.9 Hertz, what we are doing is we are heating and we are cooling down, and we let all the system to arrive to thermal equilibrium in all the moments. It means that when we release all the power, the temperature of the membrane is the temperature of the frame. We are letting the system to arrive to equilibrium. No? That essentially means that, of course, if we are able to proceed and to do a kind of a sweep, no, and a spectral analysis of the delta T 2 omega versus delta TDC, we can extract also the heat capacity from of the film from that information. But for that experiment that we wanted to measure the thermal conductance in real time, we had to fix at that point, no? Because at that point we were able to extract the delta TDC, the same magnitude that Bokley was using from DC measurements, from the AC measurement, no? Right here. Of course, there is a problem. If we want to monitor during a growth, we will be changing the heat capacity, no? And how much that will affect our measurement. This is something that we can easily model, and this is done for TPD. I will show you what is TPD later on. TPD is a whole injector, is an organic molecule. In that case, it will be a film made of a set of organic molecules, no? And the idea, the idea is that as soon as we increase the sample after and before the position, here is the 10%, no, the ratio between T2 omega and TDC. No? If we are at frequencies of 1 Hertz or below, the discrepancy, the mismatch between the two variables that we want to measure is very low. No? Then here you can see an image in 10% of, I can say error in that case, because it's not uncertainty, it's an error. No? We can correct that because we know that if the amount of mass is increasing, that can be corrected. But it's something that we have to take into account because it can introduce a kind of artifact in our measurements. This is a characteristical measurement. Here we have three different silicon nitrides. This is the measurement of Sicora, no, the one that that was published in Olivier Bourgeois in 2012. This is an out-of-plane 3 omega method of silicon nitride. This is one of the measurements that we get with our 3 omega, and this is just okay. In all of them, we have the signatures that we expect because it's an amorphous material. No, this other silicon nitride, the one of Sultan, it was I would say polycrystalline, and we had a kind of peak. Then we were expecting, we have not only a very precise method, but I would say in order to check which is the validity of the method, how much we can, which is the exactitude of the method is quite exact also because, okay, at the end, there are different silicon nitrides and somehow difficult to compare. No? Could we use that method in order to study materials? I've been already introducing, sorry, I'm touching the microphone. No, here there is an example. This is a physical review materials, an article that was published in 2018. This is a material, this is TPD, that is, let me do not try to not even read the name of the material. It's a Hall injector. It's a material, it's an organic material, an organic semiconductor that is used as a transport layer in organic electronics. And in our group, I will also put, I will introduce that in our group we have a large part of the group is working on ultra-stable glasses, and this is one of the materials that they were studying at the moment. And this type of materials, depending on the temperature, on the deposition temperature, they have different. They grow with different densities, different molecular packaging. They can play with anisotropy. They can play with the other parameter, also the thermal and the kinetic stability. That is the main point of that ultra-stable glasses. I would say the experimental setup is very simple. We have, in order to do that experiment, we require to have the chips always at very, I would say, a very controlled temperatures. We have everything is custom built. We prepare everything, and the idea is that we have a plate that is controlling temperature within a few millik's. In that case, they are typically controlled with a set of high resolution sources and meson and SMUs, and we can get temperature control around 1, 2, 3 millikelvin, and the material is evaporated from a thermal evaporator. It arrives in vapor phase, and we can monitor with a quartz crystal monitor the amount of material that is arriving to the system. This is the first measurement we did, and we get a nice surprise, no? Because here in the point 1, you can see, okay, we are starting to grow the islands. This is the thermal conductance of the empty membrane. As soon as we are starting to grow the island, to nucleate the islands on top of the membrane, the thermal conductance, it means I'm not speaking about thermal conductivity, the thermal conductance of the membrane, instead of growing, it starts to decrease. No, there is a kind of we were considering there is a kind of scattering at the beginning, but it's a kind of a rattles effect that we have. All the phonons are losing time in the islands, but it was something pretty evident. But okay, we were adapting at the beginning. It can be related with emissivity and so on. This is the first effect, no? Sorry. No, this effect that is finishing at 2.5. No, it was clearly related. This is just an image taken from a sample that was just frozen at that point. No, we were, in order to check if it was related with emissivity. Emissivity, of course, it will be proportional to the temperature. And what we did is just to repeat the same experiment at very low temperature. At very low temperatures, it means nitrogen temperature for us. No, and we were getting more or less the same reduction. It was not at all related with emissivity. It was the point that we wanted to check. No, this depression on the thermal conductance is a physical effect that can be related to that kind of scattering of the phonons that are traveling through the nitride, and they interact, they scatter with the islands. In order to check, then in the second range, from in the area in the range in the region 2, what we saw is that we start to grow the islands. We start to grow the islands, and they start to coalesce up to the region, the region up to the limit of the region 2, where we have a minimum thermal conductance, and then we enter in the third region, and the third region we identify it as a region where the islands start to percolate. This is a Hall injector. It means we could check in parallel. What we did is to check the electrical conductance, not to do that experiment that we were mentioning at the beginning, just to proceed with an electrical conductance measurement in parallel with 2 electrodes, and we saw that more or less here we find at 2.5, here at 2.6, we had the crossover behavior between the thermal conductance of the substrate, and when the islands start to percolate, that the electrical conductivity starts growing very fast. Of course, at the end, once all the islands have fit one to each other, the films start to grow vertically in 2D, and the key point here is that from that slope we can extract, because that slope is we can extract the thermal conductivity of the film. Taking the slope of thermal conductance versus thickness, we can extract the thermal conductivity, and we did it. These are 2 samples, as I said. TPD is a material, is an organic material that it has been grown. Here you have the specific heat capacity. Here there are different. This is the conventional glass, and these are different ultrastable glasses grown at different deposition temperatures. The larger appears the peak, the larger is the stability of the material. And we have what we knew from other publications is that there is maybe an implication between the stability and the order of the molecules. Then we decided to check if we were able to detect to measure that thermal conductance dependence on the between the order of the molecules in the film and the thermal conductance. Here you can see a couple of the measurements. This is when the sample is deposited at 267 degrees, and here it is 304 degrees. And the thermal conductivity extract from the slope were around 0.14 and 0.13. And I would say that here the uncertainty is in the third digit. Now, this is a very low thermal conductive material. This is for a 100 nanometers thick material, if I remember well. And even though we are able to determine with three these 3 digits the thermal conductivity of the material. Here we can see the different experiments for different, here the deposition temperature as a function of the glass transition temperature. And we can see how it was evolving. In the backside of the graph, you can see this is the order parameter for the same material studied from optical methods. And here we can see how the thermal conductivity measured with that methodology follows the order parameter. It means when we had, this is the ratio, the reduction of the thermal conductance compared to the 335 that we have around 50% of reduction, and we were able to measure up to here, and to follow that, of course, thermal conductance and the order of the molecules in the substrate, they do have a system. This is not the thing that we have been studying with that method, because we have been trying just essentially to check that initial depression of the thermal conductance. We have been trying with materials. I would say most of the materials that we have tried are materials. Softer means with the dispersion relations less tight than not the silicon nitride, in order to see if there is that rattle effect on the system. And this is the example of indium. Sorry, this is an indium sample evaporated on top of the material. Indium is well known to be a bad material, no, to be deposited on top of indium, because it does not wet. In fact, we can see here that up to, if we try to do in a pure silicon nitride substrate, we can see that up to close to 300 nanometers, we cannot find the two-dimensional growth vertically. And what I feel more interesting is that at the beginning, we can see also that depression on the thermal conductance. That is, I think it's technologically interesting, because we can envisage to use that effect to improve thermoelectric materials. We that technique to measure phase transitions. This is, I would say, a more preliminary result. But in our group, in the past, we were studying cobalt oxide, and cobalt oxide is an antiferromagnetic oxide that has an yield temperature around 290 Kelvin for bulk materials. And in our case, if we have it nanocrystalline, we will expect a very low K. And our question was, what will happen over Tn? And we will be able to monitor the phase transition. This is the phase diagram. Typically, we grow the cobalt oxide oxidizing cobalt during flight, evaporating a metallic cobalt and oxidizing cobalt during flight. And we were getting that kind of samples, that are vertical columnar growth. And here you can see one example of nanocalorimetry in that case, where we can find the delta transition that is related with the order disorder in the antiferromagnetic to paramagnetic phase. No? The first thing that we saw is that as soon as we do thermal conductance, and this is the conductance of the membrane, no, and we start seeing, we could see something small here because this is 50 nanometers. We expect to have a small depression on the temperature, on the nil temperature. And what we saw is that we start to see a huge increase. We get excited, but finally we realize that because something that may happen, that it was related. We have a highly nanocrystalline material with a lot of grain boundaries, with a lot of oxygens that may be out diffused, and this is related with the reduction of the cobalt oxide by itself. But if we pay attention in a sample without going so high in temperature, if we pay attention in a sample at low temperatures, around the phase transition temperature, what we saw is that we were able also to, with less resolution, of course, than nanocalorimetry, but we were able also to follow the phase transition, the delta transition, through the thermal conductance. Something that, okay, in that case, I would say mean free path of phonons in that kind of materials will be more or less constant because of the grain size, and this is essentially linked with the change on heat capacity that we can monitor. And I wanted to summarize. I hope I've not been too short, but I wanted to summarize the talk, saying that 3 omega Vauquelin method at low frequency. Using 3 omega Vauquelin method at low frequency, the sensor shows an exceptional resolution, and I'm placing here as soon as we are measuring measuring thermal conductance, we have to introduce the thickness in order to give the resolution. The combined resolution is below 0.065 watts meter Kelvin per nanometer. It does mean that if we were able to take atmospheric air, at 1 atmosphere, and confine it in a nanometer, and put it on top of the sample with a good thermal contact, we would be able to measure it. The point is, I'm pretty sure we will be able to measure 2D materials. The bad part of that method is, of course, we will be in contact. No, it will not be suspended 2D material. But we have demonstrated that phonons can be used, of course, as a sensitive proof to monitor real-time evolution of a filmic microstructure during growth, from the incipient clustering to the continuous film formation. We have shown also that the resolution in the thermal conductance of the method enables to detect the changes in molecular orientation, as we have shown for TPD. And at the end, we have measured cobalt oxide, and we have detected that over TNL, the thermal conductance channel is activated, but maybe it's activated because we are reducing cobalt oxide and we are getting metallic cobalt that is quite more conductive, and that the phase transition also appears on the measurement. And just to finish, I would like to thank, of course, Javier and Libertad, that are the two main collaborators in fabrication and science, and the 3 PhD students that they were in charge of doing most of the experiments, and that's all. Thank you for your attention.
Okay, thank you very much for this very nice talk. So, let's see if there's any questions from the physical audience. Maybe I can start with a question. So I have a question about these measurements where you have a 3-digit precision on the. I think it's for this whole injector. You show results as a function of temperature, where I think you also added some error bars that are quite a lot larger. So is there also some kind of structural error or uncertainty?
No, the point is that on thermal conductance we have a huge precision. On thermal conductivity we have to introduce the dimensions, and therefore the thickness is typically the limiting, because in order to translate to thermal conductivity we have to induce which is the thickness, and our error bars are always linked with error bars.
So mainly the thickness is the.
Mainly the thickness, yeah. Because on horizontal, I would say horizontal precision, we have close to 3, 4, 5 digits
right.
Also.
Ah, that's interesting. So for 2D materials, where you have very good.
For 2D materials, I would say is well treated, because we will have no discussion of the thickness at that point. We will have 1, 2, or 3 layers. But,
exactly. Yeah. Okay. Interesting.
Yeah, so somewhat related to this previous question, to the first talk. So if I'm not in mistake, you always kind of assume that you have a diffusive mechanism for heat transport, right?
Yeah.
So what happens if you don't actually in your sample? Can you decide if the experiment is addressing something, a system in which diffusive transport does not occur and it's ballistic, or other kinds of transport? And how do you translate that into the error? That also implies an error in the measurement. So
it's completely true. We are assuming diffusive transport, and we are assuming thermal conductivity. Okay, we can speak about thermal conductance. Then we skip about that. But it's true that we have to assume which is the mechanism that is going down underneath. Now, if we have that diffusion, that hydrodynamic transport, or two constants or whatever, this has to be taken into account in order to provide, essentially, to make the translation between conductance to thermal conductivity.
Yeah, but besides that, I think there's something more profound, because even the fact that when you have an one omega oscillation in the input implies that you have a 3 omega response, that already assumes many things. If you have transport which is not diffusive, I think that doesn't have to happen, right? You may have other. Does that always hold for any kind of transport? I don't know. That's a question. I'm not.
I have not an easy answer, but I would expect that in terms of thermal response of the system, at least in that one, that will dominate for sure the silicon nitride, because all the systems that I have in mind for that kind of system, for that kind of phenomena, are 2-dimensionals, but I have not a real answer for that. But it's something that has to be thought, of course, because as soon as you change the
also related to those questions, but in a slightly different perspective. So you are using, or we're using, silicon nitride as the material that through which phonons propagate, at least at the beginning, till you don't have this. The mean free path of phonons in this material, this is amorphous, are generally small. Or you can have long wavelength phonons. But what will happen with this methodology if you introduce, let's say, single crystalline silicon with a much larger mean free path, that you will probably have much more sensitivity? How that will result in your measurements?
But the point is, of course, the delta T will be smaller, but we can, that experience, for example, I can show you, because that is something that can be easily, because something that we did not introduce in the methodology at the beginning, but with indium is pretty clear. No? As soon as you increase the thermal conductance of the film, the noise is increasing. But this is essentially because at that methodology we were not changing the power input in the system, and then the resolution degrades as soon as the thermal conductance of the film. This is, I think, that the idea of using that highly conductive silicon. Okay, so it's in the table, but I think it will be extremely interesting also, because if we were able to do that kind of system, if we are able to grow a 20 nanometers layer, for example, and we are able to demonstrate that instead of having a 5%, a 2%, no, here we have 3% of decrease in, because the 3% of decrease is because the thermal conductance of the layer underneath is very low. But if we have a very high thermal conductance underneath, we will have a huge depression on the thermal conductivity, besides the 20 nanometers, besides the size of this rattling. If we are able to incorporate rattling effects on silicon, it will be extremely nice.
So there was an online question, but I think it was related to Pablo's question. So this was whether you can see the crossover from diffusive to ballistic or quasi-ballistic transport with this technique.
I would say for the moment with effective thermal conductance, but it's true that through thermal conductance we can, from the effective thermal conductivity. With thermal conductance, for sure, we will be able to see, but okay. I have not too much ways to answer that. That's a nice question in any case.
just to add to this, I think with the spatial temporal technique, Jake, it might be possible. So let's see. Any other questions? I thought maybe, Alex, did you have a question? Not anymore. If not, then I think we finished perfectly on time. So thank you everyone for coming, and thanks for both of the speakers. And see you in 2 weeks for the next NanoSeminars talk.